As the air passes through the engine, various adjustments must be made to its velocity and pressure. For example, throughout the compression stage, the air must be compressed, but no appreciable increase in its velocity can be easily tolerated. Another example, which we've already seen, occurs at the exhaust nozzle, where the pressure of the gas is dropped to that of ambient, and a considerable increase in its velocity results. These changes in pressure and velocity are accomplished by the different shaped passages or ducts through which the air must pass before it exits the engine. The design of these ducts is extremely important, because the efficiency with which the changes from kinetic energy to pressure energy and vice versa occur are reflected in the overall efficiency of the engine. In this example of the use of different duct shapes within the engine, it can be seen that the use of a divergent duct will increase the pressure of the air after it leaves the final stage of the compressor and before it enters the combustion chamber. This air, sometimes called compressor delivery air, is the highest pressure air in the engine. Using a divergent duct here gives a twofold advantage. First, an increase in pressure has been achieved with no expenditure of energy in driving the compressor. Secondly, a decrease in velocity has been contrived, which will serve to make the task of the combustion chamber, in keeping the flame burning, less difficult. This example, which we've already experienced, shows how a convergent duct is used to accelerate the gas as it passes through the nozzle guide vanes on its way to the turbine blades. The torque which is applied to the turbine blade is dependent, amongst other things, upon the rate of gas flow into it. It follows, then, that the faster we can make the gas flow into the turbine, the more torque we can transfer to the turbine. Logically, therefore, if we convert some of the considerable pressure energy of the gas stream into kinetic energy, it will be more efficient in imparting a turning effect upon the turbine and its shaft. When a compressor and turbine are joined on one shaft, the unit is called a spool. This diagram shows a single spool axial flow compressor turbojet engine. This type of engine was for a long time considered to be the most useful where an engine with a small frontal area was required, such as in fighter aircraft, where a high forward speed was the main criterion. There are, however, problems with the control of the smooth flow of air through the engine throughout its rotational speed range. More of this later. As it flows from the compressor, the air is fed directly into the combustion chambers, and fuel is added and the resulting mixture ignited. The resultant increase in temperature will cause the substantial increase in volume which is required. The energy required to drive the compressor, approximately 50% of the energy in the gas stream, is now extracted from the stream as it passes through the turbine. The remaining energy in the gas stream acts as thrust, as the gases pass to atmosphere via the end of the jet pipe. This diagram illustrates both a centrifugal compressor turboprop engine and an axial flow compressor turboprop engine. The output from a turboprop engine is the sum of the shaft horsepower developed at the turbine and the residual jet thrust. This is called equivalent shaft horsepower, or ESHP. The major difference between the turbojet and the turboprop in how they handle the generated power is that, in the turbojet, virtually all of the energy that remains after the compressor has been powered is used as thrust. Whereas in the turboprop, almost all the energy in the gas stream is converted into mechanical energy to drive both the compressor and the propeller. Only a small amount of jet thrust is available from the exhaust system of a turboprop with an efficient turbine. It can fairly be described as residual thrust only. Apart from this difference, the airflow through the engines is virtually the same in either case. The compressor passes the air to the combustion chambers where the fuel is added and the mixture is burnt, and because of the temperature rise, a substantial increase in the volume of the air is obtained at a nominally constant pressure. The gas is now expanded in the turbines, where a drop in the pressure and temperature is converted into the kinetic energy which is exchanged for the torque used to drive the compressor, or compressors, and the propeller through its reduction gear. The turboshaft engine can be thought of as a turboprop engine where the propeller has been replaced by a shaft. Turboshaft engines can be used to drive helicopter rotors. They can also be used in applications where a compact supply of electrical power is required, their output shaft being attached to an alternator. This is the type of engine normally used as the auxiliary power unit, or APU, on most modern transport aircraft. Most, if not all, turboshaft engines incorporate a free power turbine. A free power turbine is a turbine that is not connected to any of the compressors. This frees the turbine from the constraint of having to rotate at a speed that suits the compressor, and this gives the turbine a much wider operating speed range. The single-spool turboshaft engine illustrated here has a reverse-flow combustion chamber system. This allows the engine to be much shorter, stiffer, and lighter than it otherwise would be, but does add the requirement for a centrifugal compressor to be used in the high-pressure stage. This allows for the air to be thrown out radially, in order that it can enter the combustion chamber in the correct direction. Other than this deviation, the airflow is similar to that previously described for the turbojet engine, up to the point where it leaves the first stage turbine. The first stage turbine having converted sufficient energy from the gas stream to drive the compressor, the free power turbine converts any remaining energy to mechanical energy, which is utilized to drive whatever is attached to its shaft. The bypass ratio of an engine is defined as the ratio of the amount of air which is bypassed around the hot core of the engine to the amount of air which passes through the hot core. An engine with a bypass ratio in the region of about 1 or 2 to 1 would be considered to be a low bypass ratio engine, whereas an engine with a bypass ratio of around 5 to 1 would be considered to be a high bypass ratio engine. The engine shown here is a twin-spool, low bypass ratio engine. The airflow as far as the end of the low-pressure compressor is identical to that of a pure turbojet. But then the airflow splits into two. An amount, depending on the bypass ratio, will flow down the bypass duct, and the remainder continues into what is the start of the hot core of the engine, the high-pressure compressor. From the high-pressure compressor, the air follows the usual path through the combustion chambers and into the turbine, before it leaves the hot core and rejoins the bypass air in the mixer unit of the exhaust system. The propulsive efficiency of both the low and high bypass ratio engines is much greater than that of the pure turbojet, at the speeds normally associated with jet transport aircraft. The term propulsive efficiency is explained later in this lesson. The specific fuel consumption of both the low and high bypass ratio engines is also much lower than that of the pure turbojet. The experience which was gained by manufacturing and operating the low bypass ratio type of engine proved that engines which dealt with a larger comparative air mass flow and lower jet velocities could deliver propulsive efficiencies comparable to those of turboprops, and, indeed, a higher propulsive efficiency than turbojets operating at normal cruising speeds. The advent of the fan jet engine had arrived. This model of a triple-spool front fan turbojet engine shown here represents probably the most successful early example of this type of engine, the Rolls-Royce RB211. The air enters the intake and passes immediately into the low-pressure compressor, more commonly called the fan. Here, its pressure is raised before it splits, to go either through the bypass duct or into the intermediate pressure compressor, the amount going into either depending upon the bypass ratio. The thrust of this type of engine is almost completely dependent on the relatively cold air going through the bypass duct, which has a high mass and relatively low velocity, hence its high propulsive efficiency. The air which passes through to the hot core, which consists initially of the intermediate and high pressure compressors, has a great deal of energy added in the combustion chambers. But this energy is required to drive all of the compressors, which includes the fan. In fact, it is the rearmost turbine, or the low-pressure turbine, which is responsible for driving the front fan by extracting virtually all of the energy that remains in the gas stream. If it's efficient in doing its job, then there should be only residual thrust remaining where the hot gases emerge from the turbine. We previously explained that thrust is the product of mass times acceleration. It can be demonstrated that the same amount of thrust can be provided either by imparting a low acceleration to a large mass of air, or by giving a small mass of air a large acceleration. In practice, the former is preferred, since it's been found that the losses due to turbulence are much lower and the propulsive efficiency is higher. In this graph, the levels of propulsive efficiency for several different types of gas turbine engine will be shown. The highest propulsive efficiency at low airspeeds is offered by the turbo-propeller combination. However, above about 350 miles per hour, the propeller's efficiency drops off quite rapidly due to the disturbance of the airflow at the tips of the blades. In comparison with the turboprop, the propulsive efficiency of the pure turbojet appears quite poor at the lower airspeeds. As the airspeed increases in excess of 800 miles per hour, however, the propulsive efficiency of the turbojet starts to improve beyond the capability of the turboprop engine to match it, and from then on there is no comparison, the eventual outcome being a propulsive efficiency close to 90%. Cruising speeds in the order of 800 miles per hour are at present out of the reach of most transport aircraft, and this fact means that in the mid-speed range, where most of the world's jet transport aircraft operate, there is a niche for the bypass engine, both low ratio and high ratio. The low and high bypass ratio engines, which includes the ducted fan or turbofan engine, have a propulsive efficiency which fits neatly between that of the turboprop and the pure turbojet. By dealing with comparatively larger mass airflows at lower jet velocities, the bypass engine attains a propulsive efficiency which exceeds that of both the turboprop and the pure turbojet at the speeds normally associated with jet transport aircraft. The use of larger and larger aircraft has meant that more passengers can be accommodated in each flight. Thus, air travel has become less and less expensive for the individual. This concept of using large aircraft works well, as long as the aircraft themselves remain serviceable. If, however, one restricting component, such as an engine, becomes unserviceable on a large aircraft, then the expense involved in keeping 300 or 400 passengers fed, accommodated, and happy becomes exorbitant. Engine manufacturers, in an attempt to minimize the financial burden imposed upon the users of their equipment in the event of its failure, have started to use modular construction methods, which facilitate changing sections of an engine rather than the whole engine. This diagram shows how the engine is split into several modules. This concludes the introduction to the gas turbine engine.